All right, so we got an answer of 4. Now, I shouldn't say equals, that's approximate. Okay, so y of 2 is approximately 4. Okay, 10 steps would be better, and we're going to do that on the calculator here in a second. Now, another question that may come up in the homework, probably not going to ask you this on the homework, or excuse me, on the test, but it's going to come up in the homework, is, okay, verify that this is a solution. Because what they're going to want to do in the homework is they're going to want you to compare your approximation to the exact value, just kind of like we did with Aries, right? They want you to compare the two. Well, so they may say, hey, show that this is a solution, and then you can compare your answers. Well, remember when we did this, we did kind of a T-chart, right? Now this one would be really simplistic. Y prime equals 2x. So probably not going to be on the quiz because we quizzed on this before, so I'm not that interested in it right now. I mean, I hope we can do it. But what's y prime? Well, y prime, we do the derivative of this, that'd be 2x. So we plug that in over here, and we're like, oh, yeah. Now that was so ridiculously easy, it seems kind of silly to even do it. But yeah, sure, it is. We'll do one that's a little trickier later, and we'll talk about that. But that's on the homework, sometimes they ask about that. All right. So here we got 4 as our solution. So let's go to our calculators now. Everybody needs a calculator. And you're going to have to be able to do this. Okay? So less than 10 steps on Euler's method, we're going to write it out by hand, which is like that table. Okay? All right. Go into your graph screen here, Josiah. Oh. All right. We'll see. We'll see. We'll see how long it'll make it. Be a good experiment. Probably doing this is going to drain it. But, all right. So somebody else make sure you're logged in. Okay? Since everybody went flying up here, putting away their things. Thanks a lot, Allie. All right. Are you? Okay. Now, first of all, let's go into the function mode. Go into your function mode. Make sure you deleted out any of the other graphs you have. Okay? In the graph entry, if you hit tab, make sure you got all the other ones out of there. Okay? Which won't be a problem in the quiz because those won't show up when we're in the test mode. All right, now let's go to menu, and this time we're going to go to graph entry, number 3, and we're going to go down to differential equation. Okay? Now, it says y1 prime, right? And let's put in our differential equation, which was 2x. Now, sometimes you're given, like in the homework, they're going to have t is going to be the input variable. But notice right here, the calculator wants x. So on the quiz, if I give you t as the input, you have to put x when you go into your calculator. Okay, so make sure you do that. All right, so now we got that. Now let's put our initial condition in there, which was 0, 1. And go ahead and hit enter. And what it's going to do is give us a slope field, and it's going to put kind of that solution in there. Now, remember, we said it was x squared plus 1, and that kind of looks like that, right? But notice it's not connected. It's just a bunch of dots. Well, that's because it's doing Euler's method to come up with these points. That's how it's doing it. Now, let's go into our window here, Josiah, and let's set that from, what would we set our window from? Our x's. 0 to 2, right? 0 to 2. That's what we care about here. Okay? So let's go 0 to 2, and let's do a zoom fit on this. Now, actually, we probably wouldn't have to go ahead and do it, but in your window, we probably wouldn't have to just because it looks like we can see the whole graph, but sometimes you are not able to see it. So let's do 0 to 2. Now, gosh, it did it again. Like clear to 11? Yeah, why is it doing that? That's weird. Go back to 0 to 2. This other one we're going to do here in a minute, it didn't do that, but it did this last period too, and I'm not sure what's going on. Go 0 to 2 and let's see what happens. No, that's terrible. All right. Well, let's set your, go to your window settings. Let's just go to your window settings and let's just set the Y. Just go to your settings and let's go 0 to 2. This is a pretty easy one. Let's go 0 to, 6. This is a pretty easy one to do, just to set the Y manually. Okay, there we go. All right, now, notice it kind of follows a slope field, whatever. But now we want to trace. So this is not like where we had that area program we had to do the special thing. What'd you want? Oh, yeah. You know, we had this in the other class too, where the slope field wasn't matching, and that something's going on with the calculator, so don't worry about it. Yeah. If your slope field doesn't seem to be matching the graph, don't worry about it. We don't really care about that. Well, all we care about are the points here. Okay, so now we're going to trace. Okay, so this is how we do this on the calculator. Now, oh wait, before we trace, I'm sorry, I forgot one thing. What we haven't told the calculator is how many steps. Right? Our step size here was 0.5, right? We've got to tell the calculator how many steps. So go back into your, just hit tab and get into where you entered your thing. So everybody's got to be able to do this, because on the quiz, if it's 10 or more steps and you get to use your calculator, this is what you got to do. You got to put it in and you got to be able to trace. Okay? So go, is it dying? Okay, arrow up to the, okay, so get back into here where you entered your calculator, and you need to click on this. Now you can tab until it's highlighted and hit enter, or you can use your trackpad to get to it. But those 3 dots is what you need. Okay? Those 3 dots. You use your trackpad, or you can tab until it's highlighted and hit enter. Now, first thing you get here, it says Euler, solution method. Does everybody say that? Now, click on that, or right arrow on it while it's highlighted, and notice you got 2 choices, Euler and Runge-Kutta. Okay? Runge-Kutta. Think of it, that's another approximation technique. Think of it this way. Think of Euler as like left rectangles, and think of Runge-Kutta as Simpson's method. Runge-Kutta is way better, more accurate, okay, for a small number of subdivisions, but much more complicated, okay? The calculator can do it for us. We're going to do Euler because that's the one that's on the AP syllabus. Now, it's actually not going to be on, for us, for the class you're in, actually in a couple of years it's going to be on the AP test. It's not right now, so that's why you don't see it in the package. But we still do it. It's something you'll have in calc class when you get to college. So we're going to stick with Euler. It's just simpler and it fits with what we're doing. So go on down. So you shouldn't have to change anything. I don't know what I don't even know what that does, so we'll just skip that. Plot start, plot end, I have no idea. Right there. And field resolution, keep that 14, but plot step, that's the one we want. Plot step, that's where you put your step size. So change that to 0.5. Okay, and hit enter. Now what you'll notice is, and then hit OK, hit enter again. And you'll go back to your graph, and notice you got a lot less points. You got a lot less points, because it only calculated the 0.5. So now let's go to trace. So you got to be able to put in your differential equation, put in your step size, put in your initial condition, set your window, and then trace. Okay, just hit graph trace, and now go back to 0, just arrow back to the left twice. Okay, and these points should look familiar. 0, 1, now go to the right, 0.5 and 1, go to the right, 1 and 1.5, keep going to the right, 1.5 and 2.5, go to the right one more, and 2 and 4, which is what we had just come up with. Now, if we go back to the problem I had up here for us, okay, we already knew that, but this is a problem we'd be using our calculator for, right? 10 steps. So what do we need to change? And how do we change it? Right, but what will it be? Right, but what will it be? 2 minus 0 divided by... A lot of people have trouble figuring out where the 2 and the 0 come from. Again, it comes from these x values. We're starting at 0 going to 2. So we're going to go a distance of 2, and we want to do it in 10 steps. 2/10, which is 0.2. So, Jai, hopefully you're on top of it here. Or maybe the calculator is just really slow, because it's dying. It's on its last breath. Okay? So we want to go back to the dots. Our initial condition doesn't change. Differential equation hasn't changed. We're going to go down to the bottom, and we're going to change our 0.5 to a 0.2, which means we should get more points, and they're going to be different now. Okay? Go back. Yeah, let's trace. Let's just arrow back for me, because that's when we're interested. Go back to 1, right there. Okay, now remember, what did we have before at 1? It was 1.5, right? Well, now it's 1.8, because we were doing better as we went along, right? We had smaller steps. So keep going out to 2, and we're at 4.8. What happened? Disappeared. What in the world are you doing today?
Keep arrowing to the right.
And it just keeps jumping back. Try just typing in it too. There you go. Huh, that's weird. I thought you were doing kind of like I do with laundry. I just screw it up so much that my wife eventually says I can't do it anymore. So I thought you wanted to not be the presenter anymore. All right. So notice 2, 4.6. So instead of 4, remember the right answer is 5. So we're getting closer, right? It's a better approximation. If we did 20 steps, 30 steps, whatever, it'd be even better. Okay? There it is. That's Euler's method in a nutshell. Okay? So let's go through one where we have to do it a little bit more by hand. All right? And you can write this down, be good practice, and then we'll talk about what your homework is, and we can go from there. All right, so I've set this up already for you. And I was gonna plot the points, but I may not do that. So I can give you some work time here. But here would be, this is a Newton's law of cooling. Hopefully that sounds familiar to you. We've got a differential equation, y prime equals k, y minus big T. Big T was the room temperature, that kind of thing. K here's negative 0.1. So this would be like room temperature is 70. The coffee's 190 degrees to start. Okay, this would be that situation, right? It was Newton's law of cooling. But anyway, it's a differential equation. We're going to start at 190, and we want to know 5 minutes later how hot's the coffee. Okay? So, the only thing missing I haven't told you yet is what? How many steps? So let's say I told you this was going to be 5 steps. Now we're going to write out a couple of them, and then I'll fill in the rest from the book. This is actually right in the book. But once you get the hang of it, you'll get it. We don't have to sit here and do it all day long. So I'm going to tell you 5 steps. So that is your signal. Oh, I got to do this one by hand. Okay? So 5 steps means the step size, the delta x is going to be 1. Right? That'll make it our calculations easy anyway. Okay? So the step size is going to be 1. So we start over here with our initial condition. Right? So there's our starting point, 0, 190. So the next thing we got to calculate. Now, yeah, you can memorize the table. That's fine. But again, I also want you to understand what it is you're finding. I think on the quiz, the one you do by hand, I think the table's the best way to do it because I want to see these calculations. Okay? So I think writing it out as a table is really the best way to communicate that. Okay, so the slope, what do we do? Now this one has a y in it. Our last one had an x, right? You might get one that has an x and a y, or a t and a y, so you'd have to plug both in. But we plug in 190 minus 70, so get on your calculators. If you need to, that'd be 120 times negative 0.1. What's that? Negative 12. Negative 12. Okay, so that's our slope. Now how do we get the delta y? Multiply by your step size, right? This is the rise over run times the run. That's the key step. Rise over run times the run. Well, our run is 1. That's nice. So, since we're going over 1, we're going to go down 12. That means the temperature dropped 12. So our new y is 190 minus 12. 178. Now, next line. Oh, and here's what I normally would do when I'm doing this table. Once I figured out my step size was 1, I usually just fill in the x column right away. I just can fill in these just because sometimes I get, when I come back to the next line, I'm like, oh wait, what's my x? And I forget that. So as soon as I know my step size, I just fill this in. If my step size was 0.5, I would have went 0, 0.5, 1, 1.5, so forth. Okay? All right. So now my new y is 178. All right, so now I got to plug that in. Let's do that. Let's do a couple more lines here. So 178 minus 70 times negative 0.1. Negative what? 10.8. So that's my rise over run. I got to times that by my run, which is just 1. So that's easy. So that's negative 10.8. So this time I'm going down 10.8. So it's not going down as much, right? As it cools, we know it does slow down. If I was going to graph this, we know that it would kind of go, like this, and it would start leveling off. right? Okay, so negative 10.8. So I subtract that from my old y, which was 178. I get 167.2. Let's do one more line, then we'll just fill in the rest. So now I'm at 167.2 degrees. Figure my slope. Negative 9.72. Times that by 1. Still negative 9.72. So I drop my temp down again by that much, and it's going to go down 157.48. Okay. And now I'll just tell you what the rest of them are, and you can write them in, and then you can go back and review this. This could be one you could kind of review as part of your homework. But the next one, the next slope is negative 8.75. And when we subtract that, we get 148.73. Okay, and the next one is negative 7.87. I'm not going to ask you to do like 8 of these, probably. 4 or 5 is probably the tops, but because once you can do 1 or 2 lines pretty good, you're probably good. Then you're just going to screw something up finally if you do too many. All right. So there is our final answer, 140.86. That's an approximation. At 5 minutes, the coffee would be approximately 140.86 degrees. Okay, but it's using this kind of the same concept that we did with our rectangles as far as how we approximate. We take the information we have and we work with it, even though it's not exact, because we're making this assumption that the slope would stay that same the whole time. Okay, so let's go to the calculator. Uh-oh. It's gone. All right. Oops. Oh, geez. Thanks a lot, guys. Got like nobody logged in. I'm going to get somebody. I'm going to get somebody who's not logged in. Oh, well. Brock, you still logged in?
Yeah.
All right. Bonus points, man. Way to go. Bonus points. 30 bonus points. Yours, yeah. Jeez, you guys got a quiz on Friday where you need your calculators. See, here comes
It does this every time I'm playing. It's good.
You're good? Yeah.
Good.
Sure you are. Jesus is so. Yeah, it's good. Carly. Oh, she's plugged in. She's plugged in. All right. Go to your differential or your graph. Let's go to the graph screen. Now let's do this with 20 steps. 20 steps. So you have that one. Oh yeah, let's go back and type in, right? Everybody, let's go back and let's type in this new one, right? This will be good practice because there's something that comes up here we really got to talk about. So she's typing in negative 0.1 parentheses y minus 70. She's putting in her initial condition. Now hold right there. Don't do anything else. Now, she put this in wrong. Okay? But she did that because I told her to ahead of time. I told her ahead of class to do it wrong. So I can talk about this. What's wrong? This is y5 prime. So what does this need to be right here? That's got to be y5. Now, if you guys are putting yours in y1, then if you're at y1 prime, then this needs to be y1. Okay? And they do that because you can actually do differential equations where you can reference different y's. It's kind of a strange deal. So that's why that's in there. Okay? So you would have to, so, and I'll try to remind you of that when we're doing the calculator ones. Okay, when you type this into your, but I may not either. Okay, if you're at y1 prime, when you put this in, and it's got a y in it, you got to put y1. Okay, or y5 or whatever the case may be. All right, now let's go ahead. What's our step size? 20 steps. Yeah, we could do one and then match it, but what would it be? A quarter, right? We're going from 0 to 5 in 20 steps. So 5 divided by 20 is 1/4 or 0.25. So we've got to go down to our step and we've got to do 0.25. Now your plot start and plot end are weird. I've never seen those numbers. Did you ever change those? No? Okay, that's weird. Well, let's just see what we get. Okay, so go ahead and hit OK. Now, here we notice that we can't see it. Right? So let's change our window. So we need to go 0 to 5. And I think, now in the other class, Zoom Fit worked kind of good here. So if you go 0 to 5 and do a Zoom Fit, this actually worked out pretty well for us. Yeah, there they are. Your slope field's gone? Try entering it in again or just, okay, what'd you do?
Well, one deleted out. When I typed Y1 the first time, couldn't it just remove it?
Oh, you had to put it back in. Okay. All right, let's trace on this, Carly, and let's go. Now, did it? Oh. It kind of screwed up again on us, didn't it? Well, but that's it too. It should be 0 to 5. Didn't you put in 0 to 5? Go to your window again. It does kind of change it after you do the Zoom Fit, doesn't it? But you can still get there. You can just, because really all you guys need, I'm having you trace and look at all the points, but all you really need is 5, right? To answer the question, all you need is y at 5. So you can go to trace and just hit 5 and boom, you're there. So it really doesn't matter on the window setting. I just want us to be able to see it. I mean, just to answer the question, though, we really don't need it. So like right now, she could just type in a 5, okay, and hit enter, and it's going to redraw the graph and give it to you, I think. Do it again. Type 5. There it is. Okay, looks like you might have to do it a couple times. I don't know. But, okay, there it is. Now, what did we have before? 140 point something? Yeah. Right? Because we knew it was dropping, but it was dropping too fast the way we were doing it with one step. Now it's not dropping quite as fast, more accurate. So now we're saying it's 142.323. And so now you can give that answer for 20 steps. So when I say use the calculator, right, if you have 10 or more steps for Euler, it's graph the differential equation, put in your initial condition, set the step size, and then trace to the place you want to be. Okay? That's how we do this with Euler's method. All right. So your homework, there's going to be some like that where you're going to get to do maybe a table. Probably do that a couple of times in the homework. And then the other. Oops, I keep going. All right, last thing. So if you had one like this, so if they said, okay, show that this is a solution. I just wanted to show you one real quick. There's a little bit of this in the homework. Probably not going to make a big deal of this on the quiz. I am thinking about having a bonus on there, so that would be where this could come in. So show that this is a solution. So we do like a T-chart. So over here we'd have negative 0.1. In place of the y, we'd put 70 plus 120 e to the negative 0.1 t. And then you got the minus 70 over here, right? So I just plug that in place of the y right there. Over here I need y prime, so I do the derivative of this. 70 would just disappear. This is its own derivative, but you'd have to kick out a what? You have to kick out a negative 0.1. Now negative 0.1 times 120 is negative 12. So that derivative would end up being negative 12 e to the negative 0.1 t. Now you actually get to use your calculators here, so you could actually just have the calculator do that derivative, right, for you. And then you've got this. Well, what happens here? The 70s cancel. You take negative 0.1 times 120, which sure enough is negative 12 e to the negative 0.1 t. And so, yep, they match. Right? That's how we did that. Right? Show that this is a solution to the differential equation. We plugged it in for y. We plugged the derivative in for y prime. We showed that the two sides were equal. Okay? So if you see some of that, that's just old differential equations. All right. Let's talk quickly here about the quiz. Okay? All right. Now, so 6.1 is where we had those written out versions of left, right, midpoint, trapezoid, and then we learned about Simpson's rule. It had the 4-2-4 pattern, right? 1 at the beginning, and then 4-2, 4-2, and then 1 at the end. Be able to draw rectangles, trapezoids, midpoint rectangles. Be able to write them out if you have less than 10, right? If I ask for a T4, pretty much guaranteed that's going to happen. You know, an L5, S8. Use a short, I don't know if they're really shortcuts, but those other formulas we had for Simpson, right? S8, right? Or a trapezoid, you can average the left and the right, right? You could do those if you want. So be able to calculate those out. Now, if you have 10 or more, we're not going to be able to use the area program because when we're in test mode, it's not going to let us. I'll just give you what you need. For example, let's say what I might do is give you an L10, R10, M10, and T10. Just give it to you. And then say, find S20. Show your work. So what would you do for an S20? 2 M10s plus a T10 divided by 3, right? So that's how I might ask you one of those where we can't use that area program. I'll just give you the ones, but I might ask you to do something with it like that. So that might be an example, okay? But otherwise we won't have that access to that area program. So mostly it'll be ones less than 10 where you write them out. Now, if we scroll back to that real quick, so I'm talking about this, right? This stuff here, which is, you know, you've had in your notes for a while. Simpson's rule, remember it's b minus a over 3n, so you might look that over, right? Now, if you don't want to use that, maybe you want to use this, right? Maybe you want to use this, right? If you had to do an S8, maybe you'd rather do your M4, your T4, and then do that formula. Fine, whatever. Okay, but we have those. All right, then the next thing that was in 6.1 was that over-under approximation stuff. Over-under approximation. Okay, so if it's increasing, lefts are under, rights are over. Decreasing, rights are under, lefts are over. Right? And then the concavity, trapezoid midpoint, how concavity affected that. So be able to answer those questions about over and under approximations. Okay, so that was basically it, 6.1. 6.2 is when we had the max error formulas with the K1 and the K2. Right? Got to be able to use those formulas. Here they are. Okay, here they are. Now, and I'm giving you these. Now, what I won't give you is the underlined part in red, right? You got to know that. You got to know that K1 is a max of F prime absolute value. So you find F prime, you graph it, find the max, right? Graph F double prime absolute value, find the max. And then round it, bump it up if you have to, and show your work. Show your work, right? So I can see what you're using for the K1 and K2 values. Should be pretty straightforward. Now, how would I ask that? Well, I might say, use the formula to find the max error. Well, right, that's what I want. It's that number right there, right? Sometimes it says find the error bound. Use the formula to find the error bound. Well, that's what this is the error bound, right? So I don't really care if you write this side of it. I really just want this, right? The max error is really what I'm after. Now, technically, error bound really the whole thing should be written out. Error bound for T4. So could be I minus T4, less than or equal to that number. But that's not really what I'm grading on, is really finding that number. So, but show your work as you set it up. We also talked about how you could then add that on and take that off of the approximation, and that the integrals in between there somewhere. So we said you could write it like that, but that's not a big deal. Okay, so that was really it in 6.2. All right, and then 6.3 was just exactly what we did today, Euler's method. You got less than 10 steps, you write it out kind of with that table. It'll look just like we talked about. Here's a differential equation, here's initial condition, now find y of 2, y of 3. Go through the steps. If you have more than 10 steps or 10 or more steps, then we just put in our calculator, put the step size in the calculator, trace out to that point, write it down. That's about all it'll be. Okay? And then you might have some questions, that just how does this work? Like we talked about max error formulas. Why K1? Why the max of F prime? Well, because that's the steepest slope. That's what causes the error. We're going to assume it has that slope the whole time. That's the most the error could be. Same with concavity. Right, so be able to maybe answer questions about that. That's it. Doesn't seem too bad, I don't think. Okay? All right, so for your homework, it's going to be Friday. It's going to be Friday. Okay? And like I said, and I won't be here tomorrow, but I will be here in the morning. Thursday, be here Friday in the morning, be here at lunch on Friday for the quiz. So if you've got some questions. I'll have the answer book here tomorrow with the sub. I'll have some problems. I'll put those up here in a little bit. So if we look at the assignment, and I'll let you get started on it here. Let's skip 1 and 2. Start, I think, the best option would probably be to start with number 11. Because number 11 is kind of just a basic problem with Euler's method where you got to do all the different things. So if you start with 11, it would be very similar to what we just did. So they'll give you a differential equation with initial condition, have you do, I think, 4 steps first. Then they'll ask you to do 10 steps. So you do one by hand, do one with the calculator. Then they'll ask you to verify a solution, and then they'll have you compare your answers to the exact answer. Okay, that kind of thing. Now, 6 and 8, the reason I wouldn't start with 6 and 8 because they're both kind of weird ones where something kind of strange happens and they want you to explain what's going on. Okay? They're pretty simple calculations, but you'll be able to see. So I don't know if those are good ones to start with. I think it'd be better to start with 11 and go through the process first. 13 is kind of similar to 11, except you don't have to do any by hand. They're all ones you can just trace on the calculator. And then 15, I think, has one to do by hand, and then it asks you some other questions. Okay? All right, so there's your Euler's method practice, and then here in a little bit I'll put up what I'll tell the sub to give you tomorrow. But who wasn't going to be here tomorrow? You weren't going to be here, right? Okay, so I'll throw that up there so you can jot that down. It's just really work time tomorrow. Yeah, I don't think Mrs. Kinsley's probably going to be teaching you a bunch of calculus. So it's pretty much going to be work time on the packet, and then reviewing for the quiz and that.